Right now, a clock on your wrist is ticking slightly faster than a clock in your basement. You will never notice it. You will never feel it. But it is true. Time is not one thing happening everywhere at once. It bends, it stretches, it slows down and speeds up depending on where you stand. And nowhere does it bend more violently than near a black hole. What you are about to learn will change the way you think about every second you have left. You grew up believing time was steady. A second here is a second there. A clock in New York ticks the same as a clock in Tokyo. This feels obvious. It feels like common sense. But common sense was built for a world of slow speeds and weak gravity. It was never built to survive contact with a black hole. In 1915, a German physicist named Albert Einstein published a theory that quietly destroyed this assumption. He called it general relativity. The idea was strange, even to him. Gravity, he said, is not a force pulling objects together. Gravity is the bending of space and time itself. Mass whoops the fabric around it, the way a bowling ball whoops a stretched sheet. And if space bends, time bends with it. Where gravity is strong, time slows down. Where gravity is weak, time speeds up. For decades, this was just math on a page. Then, in 1959, two physicists named Robert Pound and Glenn Rebka tested it. They placed a radioactive source at the top of a tower and a detector at the bottom, just 22 meters apart, a tiny difference in gravity between the top and the bottom of that tower. And they measured it. The frequency of light shifted exactly as Einstein predicted. Time really did move slower closer to the ground, slower where gravity pulled harder. A 22-meter tower was enough to prove it. Now imagine gravity a billion times stronger. Imagine a black hole. A black hole forms when a massive star runs out of fuel and collapses in on itself, not slowly, catastrophically. All of its mass crushes down into a single point, and gravity around that point becomes so extreme that nothing, not light, not radiation, not information itself, can escape past a certain boundary. That boundary has a name, the event horizon. Cross it and you are gone. Not destroyed instantly, gone from the outside universe forever. But here is the part that breaks people's intuition. What happens to time as you approach that boundary? Picture two people. One stays far away in a spaceship, safely watching. The other falls toward the black hole. As the falling astronaut gets closer to the event horizon, something impossible seems to happen from the outside observer's point of view. The astronaut appears to slow down, not speed up, slow down. Their movements stretch out. The radio signals arrive later and later, spaced further and further apart. To the person watching from a safe distance, the falling astronaut seems to freeze at the edge of the event horizon, frame by frame, forever approaching but never quite arriving. Why does this happen? Gravity near a black hole is so strong that it stretches time itself. The same way Pound and Rebka measured on that 22-meter tower, except now the effect is not subtle. It is extreme. Every second for the falling astronaut takes longer and longer to reach the observer outside. Their clock appears to tick slower and slower until, from the outside, it appears to stop entirely. But here is the twist. The astronaut falling in does not experience this at all. From their own perspective, time feels completely normal. Their heartbeat does not slow. Their thoughts do not stretch. They fall past the event horizon in what feels to them like an ordinary handful of seconds. Two people, one event, two utterly different experiences of time. Whose clock is correct? They both are. That is the part that takes time to accept. Time near a black hole is not a single shared river everyone floats down together. It is personal. It depends entirely on where you are standing and how fast you are moving. Physicists call this relativity of simultaneity, and it means the universe does not have one master clock ticking away in the background. It has billions of clocks, all running at slightly different speeds, all technically correct for the observer holding them. This is not just a thought experiment locked away in physics departments. You rely on it every single day without knowing it. Global positioning satellites orbit far above Earth, in weaker gravity than you experience on the surface. Because gravity is weaker up there, their clocks run faster than clocks on the ground, by about 38 microseconds a day. It sounds tiny? It is not. Without correcting for that gravitational time difference, GPS positioning would drift by roughly 10 kilometers within a single day. Your phone's map would slowly, silently become useless. Engineers correct for Einstein's math every time you check directions to a coffee shop. Now scale that effect up. Not 38 microseconds, not a subtle correction on a satellite. Scale it up to the edge of a black hole, where gravity is not slightly stronger, but functionally infinite. In 2014, the physicist Kip Thorne worked with filmmakers to model what this would actually look like near a massive spinning black hole. His calculations helped visualize a moment where 1 hour spent near the event horizon of a large black hole could equal roughly 7 years passing for someone far away. 1 hour, 7 years. You could descend toward a black hole, orbit briefly, return to a waiting ship, and find everyone you loved had aged decades while you barely aged at all. Sit with that for a second. Is it possible? According to the equations, yes. Time dilation this extreme is not science fiction stretching Einstein's theory past its limits. It is Einstein's theory, taken exactly as far as gravity allows. The stronger the gravity, the slower time runs relative to someone outside it. A black hole is simply the most extreme gravity the universe has to offer, so it produces the most extreme version of this effect. But why does it matter to you, sitting here, far from any black hole, with ordinary gravity and an ordinary clock? Because it reveals something uncomfortable about the second you just spent reading this sentence. You have always assumed your time is fixed. A universal currency, ticking the same for everyone, everywhere, forever. It is not. It never was. Your experience of time is a local phenomenon, shaped by the mass beneath your feet and the speed at which you move through space. You are, in a very literal sense, living inside your own private clock, slightly out of sync with everyone else on the planet, and dramatically out of sync with anyone who ever gets close to a black hole. There is something almost comforting hidden inside this strange physics. If time is not fixed, if it bends and stretches depending on where you stand, then the feeling that time is running out is itself a kind of illusion built for a world of ordinary gravity. Somewhere in the universe, right now, near the edge of a black hole, a version of an hour is quietly becoming someone else's 7 years. Time is not a countdown clock ticking the same for everyone. It is a landscape, and you get to choose in small ways how you move through it. Right now, that clock on your wrist is still ticking slightly faster than the one in your basement. You will never feel it. But somewhere out there, at the edge of a black hole, someone's version of a single hour is quietly outlasting your entire year.